Okay, section 13.5 is going to take what we've learned about colligative properties and add just a little bit of complexity to it. You may remember when we talked about molality in the very first place, I said that molality is most often what we're concerned with is the moles of solute particles, and that's maybe a kind of a weird way to put it, over kilograms of solvent. That's the molality. And so what do we mean by solute particles? Why am I using such like cumbersome language? Well, if I have something like C12H22O11, and that is a solid, and I dissolve it into water, then I will get C12H22O11 aqueous. I will get one solvated particle for every one particle of our solute, because this is a non-electrolyte. But an electrolyte like NaCl, for example, NaCl solid is going to form Na plus aqueous plus Cl minus aqueous. Now we'll often write this as just NaCl aqueous, but it's important to recognize that if it's truly aqueous, then the cation and the anion have separated. They are not actually close to each other. They don't have any attraction toward one another. They're each surrounded by their own water molecules forming a hydration sphere. And you'll notice we get two particles out of the deal. And so electrolytes are going to give you a stronger effect on their colligative properties than non-electrolytes for the same molar amounts. In principle, so let me first introduce this formula. I is equal to the number of particles over the number of solute formula units. Right, so if I have one formula unit, how many particles is that going to generate? That is what we call I, or in other words, the I need to check this, Van't Hoff factor, with a lowercase v and an apostrophe and all of that. So the Van't Hoff factor I tells you how many particles you get for every mole of your solute. And in principle, that Van't Hoff factor can get pretty complicated because your cations and your anions, sometimes they don't separate completely. There's some small fraction of them that at least maintain some sort of relationship to each other. And it can get a bit complicated. But for this class, we're just going to say that things like NaCl have an I equal to 2. Things like sugar have an I equal to 1. If I take something like calcium chloride, CaCl2, if that gets dissolved in water, we're going to generate one calcium 2 plus ion and then 2 chloride ions. So CaCl2 is going to have an I equal to 3. And then we can look at other electrolytes, not just ionic compounds, but what about something like HNO3? This is a molecular compound, covalent bonds all around, but it is a strong acid. And so we know that in water, this hydrogen is going to be donated to produce hydronium ion. We'll have nitrate left over. And so this strong acid is going to have an I equal to 2. Then weak electrolytes, weak acids, weak bases, they're going to have a Van't Hoff factor somewhere between 1 and 2, usually quite a lot closer to 1. If they're weak acids, then their degree of dissociation is usually quite small. And so what this means is that when we have electrolytes, we need to make sure we include the Van't Hoff factor in all of our colligative property calculations. So, for example, we would calculate mole fractions for vapor pressure lowering. This would be N solute times that Van't Hoff factor over N solute times, oh, I'm sorry. Yeah, no, that's right. If we wanted to know the mole fraction of solute particles, then we would have the number of moles of solute times its Van't Hoff factor. And then over the total number of particles, again, we'll have to include that Van't Hoff factor and N solvent. Okay, and if you wanted to find the mole fraction of a solvent, you would still need to include the solute's Van't Hoff factor in that denominator, right? Because you get maybe 2 or 3 particles out of each mole of the solute that you dissolve. For something like freezing point depression, delta TF is going to be KF, negative KF, times the molality times that Van't Hoff factor. So if I wanted to lower the freezing point of a solution, if I add 1 mole of sugar, that will only have half the impact of adding 1 mole of sodium chloride. And the same thing applies for our boiling point elevation. That's going to equal Kb times the molality, but we're also going to have to multiply it by that Van't Hoff factor. And then finally, pi is going to equal N times I RT over V. The Van't Hoff factor, again, for osmotic pressure. So that's just a little extra bit that we need to consider for these colligative properties when you have a solute that breaks apart into more than 1 particle when it dissolves.